We're now going to start a new chapter in Math 5, Chapter 2, which is about sets and functions. We're going to begin by learning a little bit about informal set theory, then we'll move on to the study of functions and their properties, and at the end we'll study a special kind of function called a permutation. So let's begin with the definition of a set. Now, the informal definition of a set is that it is simply a collection of mathematical objects, and the way we write those collections is usually we write the objects in the collection between curly brackets. So the set containing 1 and 2 and 3 would be written like this. There's some special notation for the things in a set. The objects in a set are called its elements, or its members, more commonly its elements, and we write little x and then this symbol and then capital X to mean that little x is an element of the set capital X. We use the same symbol crossed out to mean that x is not an element of big X. So if I write this, then that means that little x is not an element of big X. Finally, one special set is the empty set. So the empty set is the set which doesn't have any elements at all. So we write it like this with this 0 crossed out. You will sometimes see people just use a pair of curly brackets with nothing between them like this for the empty set, but I will always use this 0 crossed out symbol for my empty set. And the point of the empty set is, like I said, it doesn't have any elements. So this, no matter what A is not an element of the empty set. Okay, we're now going to look at the idea of a subset, which is roughly one set which is contained inside another set. And our definition is that a set X is a subset of a set Y if and only if every element of X is also an element of Y. So we can introduce some notation for this as well. So let's just put this at the top here. So let's say and we write X and then this symbol and then Y to mean that X is a subset of Y. So let's see some examples of this. For example, the set containing 0 is a subset of the set containing 0 and 1. Because every element in the set on the left, every element in this set, is also an element of that set. Let's have an example of something which is not a subset. So if we take 0 and 1, that's not a subset. So we use the subset symbol crossed out. It's not a subset of 1 and 2 because there is something in this set, namely 0, which is not in that set. One final example, if I take the set, actually maybe not one final example, I'm going to do two more examples. So if I have any set, let's make this clear. So for any set X, X is always a subset of itself, because if something is an element of X, then it's also an element of X. And finally, let's have the interesting thing about subsets is that the empty set is a subset of every set X. Now, you might think that's a bit of a strange thing to say, but we regard the statement every element of the empty set is an element of this set capital X as being vacuously true because there are no things in the empty set, so there are no counterexamples. It's easiest to think about this backwards. If you think X is not a subset of Y, then you've got to find something in X which is not in Y. But you can't find anything in the empty set which is not in your favourite set, capital X, because there's nothing in the empty set, and therefore you have to agree that the empty set is a subset of every set. So let's make this clear for any set X. Okay, the empty set is a subset of every set. Now, you will sometimes in other sources see people use just the curly bit of the subset symbol. The problem with doing that is that some people use that to mean subset, and some people use it to mean proper subset, which I'm going to define slightly later. So for me, I will never use that symbol. I'll always use the symbol which I drew just here for subsets. Okay, so we're now going to define what it means for two sets to be equal. We say that a set X is equal to a set Y if, for anything A is an element of X if and only if it is an element of Y. So in other words, every element of X is an element of Y, and every element of Y is an element of X. Now that has some interesting consequences, because for example, if you look at the set 1 and the set which I'm going to write like this, then those two sets are equal, because the only things which are elements, the only thing which is an element of the set on the left is the number 1, and that's also an element of the set on the right. But the only thing which is an element of the set on the right is the number 1, and that's also an element of the set on the left. So those two things are equal as sets. And similarly, if you look at the set containing 1 and 2 like this, and you look at the set where we have the same elements but we list them in the opposite order, again they are equal, because the only things which are elements of the set on the left are 1 and 2. Now 1 is an element of the thing on the right, and 2 is an element of the thing on the right. But on the other hand, the only things which are elements of the thing on the right are 2 and 1, and 2 is an element of the thing on the left, and 1 is an element of the thing on the left. So something is an element of 1, 2 if and only if it's an element of 2, 1. So those things are equal as sets. So when people say things like set equality ignores repetition and ignores order, that's what they mean, that the set 1 is the same as the set containing 1, 1, and the set 1, 2 is the same as the set containing 2 and 1. So let me just point out that there is another way to phrase the definition of set equality, which can be quite useful, which is to say that set X is equal to Y if and only if, I'll write that just as if for short, if and only if X is a subset of Y and Y is a subset of X. Because if X is a subset of Y, that says if something's an element of X, then it's an element of Y. And if Y is a subset of X, that means if something is an element of Y, then it is an element of X. So you put those together and you get something as an element of X if and only if it is an element of Y. So that's useful because it can be handy when you're doing proofs. If you want to prove two sets are equal, which is kind of a common thing to do in mathematics, then the fact that you can rephrase the definition of set equality this way lets you split your proof into two parts. So the first part you show X is a subset of Y, and the second part you show Y is a subset of X. Sometimes useful to be able to do that. Okay, then finally, X is a proper subset of Y, if and only if X is a subset of Y, but it's not equal to Y. And the notation we use here is X, and then like the set subset symbol, but with the cross through the line at the bottom. So that's the notation for X being a proper subset of Y. So as an example, if you have the set just containing 1, that is a proper subset of the set containing 1 and 2. And it's sometimes useful to distinguish between a proper subset and just a subset. So anything is a subset of itself. For example, it's true that, let's say that, in fact I wrote it up here, that any set is a subset of itself. But of course it's not true that any set is a proper subset of itself. Okay, finally then, another piece of notation that we use for defining sets, which is called set builder notation. So in order to use set builder notation, you need one of these relations that we learned about in logic. So, a relation with just one element, with just one variable, is a true or false property about a particular thing. So let's say you've got a property, a one variable relation, P of X, about elements little x of a set big X, then this notation here means the set of all elements of capital X which make this property true. So for example, you might take your set to be the set of integers z. So remember, z means the set of all positive or negative whole numbers. 0, 1, 2, and so on, like this. Then one way we might use the set builder notation is to form the set of all elements in z such that x is even. So here the property p of x is even. That's a true or false statement about any integer. So this would be the set of all things which make x is even true. So the set of all integers for which it's true that that integer is even. So this will be all the things like -4, -2, 0, 2, 4, and so on, all of the even integers. So this set builder notation is very common, especially for sets which have an infinite number of elements, because for those things you can't necessarily list them all, you can't necessarily write them down in some easy way. So it's useful to have this set builder notation, especially when we're talking about sets with an infinite number of different elements. Now sometimes in our set builder notation we don't want to specify the set X we're talking about, so we just write X colon p of x in set brackets and curly brackets to mean the set of all things x such that this property p of x is true.